previous example essentially used an average rate of change to approximate an instantaneous rate of change, which fundamentally just refers to our second objective here. So let's try to establish some key associations that are going to carry throughout the rest of this course. So first we have the average rate of change, which is associated with the slope of a secant line. A secant line, remember, goes through 2 points, and it would be very easy to calculate that slope as some sort of rise over run, some sort of change in x over change in y. It is the same slope that we've been calculating since Algebra 1 and we first learned to do slope. It's a pre-calculus idea. However, we need calculus in order to do the second one. An instantaneous rate of change is associated with the slope of a tangent line. So a tangent line, recall, touches a graph hopefully at one point, but it's possibly it touches more if this thing kind of curls over or something like that. But it touches once over some small interval and it goes in the same direction as that curve at that particular point, and that direction is essentially the slope at that point for that graph. Now, when Newton was first cobbling together this whole thing called calculus, back in the late 1600s, I believe, here, let's pull this up on Wikipedia. Yeah, it said that it was first published 5th of July, 1687. That work is called the Philosophiae Naturalis Principia Mathematica. Insert your own Latin accent anywhere you wanna, and usually it's just referred to as Principia. So when he was putting this stuff together, and this is where we get the foundation of calculus, understand that it was within the context of physics, classical mechanics, gravity, and things like that. So we often have physics applications associated with calculus. And one of those things is going to be velocity. Common physics application of rates is an object's velocity, which is the change in position of the object over time. And that change in position, we also want to indicate the direction in some kind of way. And for us, that's usually going to be just a plus or a minus to indicate that it's going upwards, downwards, or left or right. So prior to calculus, we were able to do this concept as an average velocity. And again, average velocity is associated with the slope of a secant line. It's a change in distance over a change in time. It's a rise over a run. So for example, let's say we took a road trip, and that road trip was 120 miles, and it took us 2 hours to drive that far. We're going to average 120 divided by 2. We got 60 miles per hour for the whole entire trip. Does that mean we were always going 60 miles per hour? Probably not. It means that sometimes we were going down below it, sometimes we were going up above it. It's entirely possible that at some point we were going 60 miles per hour, but we just averaged 60 over the course of that entire trip. Okay, so now calculus is going to help us get an instantaneous velocity. And an instantaneous velocity is just like the instantaneous rate of change. It is associated with the slope of a secant line. And let's say you're on that same exact road trip and you take a look at your speedometer and it says 60 miles per hour. That is how fast you're going at that particular moment. You throw in your direction and you have your velocity. Okay, so calculus is going to help us do that. And at first, we're going to learn how to find that instantaneous velocity or approximate it with an average velocity. Okay, so here is a formula then for average velocity. I would definitely write it down. It's gonna be on our memory card for sure. It will always be on the AP Calculus exam, and it's often confused with, oh, calculus, I'm supposed to be taking derivatives and find the slope of a tangent line, when the question was actually asking for an average velocity. How do I calculate average velocity? Piece of cake. It's a change in position over a change in time. It is the slope of a secant line. However, there are also going to be questions that are going to ask us for the instantaneous velocity, which, if you see here, it's that limit notation again. It says the limit delta t as this change in time right here approaches 0. So essentially, we want this time change here to shrink down until it gets closer and closer to 0, so we can arrive at the instantaneous velocity. We are taking the limit as this time interval goes closer and closer to 0 of the average velocity. to get the instantaneous velocity. Now remember, this is what the objective is about. We're using an average rate of change in order to approximate an instantaneous rate of change. And we'll refine this process of taking the limit through this unit, this first unit that we're working on.